everything you believe to be real is a statistical anomaly. Look at your hands. Feel the chair beneath you, the air in your lungs. It all feels solid, permanent. Now imagine all of it. You, this planet, the sun, every star you've ever seen, every galaxy we've ever photographed. All of it is just a bit of cosmic fluff, a rounding error. Because the brutal, beautiful truth of our universe is that everything we can see, everything we've ever known, makes up less than 5% of what's actually out there. So what is the other 95%? It's not empty space. It's something else. An invisible scaffolding holding our galaxy together, and a mysterious energy pushing everything apart. This is the story of how we discovered that the universe was mostly missing. Our journey into the dark begins not with some grand revelation, but with a grumpy astronomer who found a problem he couldn't ignore. The year is 1933. Fritz Zwicky, a brilliant but famously cantankerous mind, is studying the Coma Cluster, a gigantic swarm of over 1,000 galaxies. He's measuring how fast they're moving, and the numbers are just plain wrong. The galaxies on the outer edges are moving at ridiculous speeds, so fast that the gravity from all the visible stars in the cluster shouldn't be nearly enough to hold them in. The entire cluster should have ripped itself apart billions of years ago. Yet there it was, stable. The math didn't add up. Zwicky did the only thing he could. He trusted his observations. He calculated that for the cluster to hold together, it needed to be about 400 times more massive than it looked. There had to be some other source of gravity, something invisible. He called it Dunkelmaterie, dark matter. But science in the 1930s wasn't ready for such a radical idea. Zwicky's abrasive personality didn't help. His groundbreaking discovery was dismissed, treated as an oddity, and forgotten for nearly half a century. The universe, everyone assumed, was just what you see is what you get. Flash forward to the 1970s. An astronomer named Vera Rubin is about to accidentally prove Zwicky right. She wasn't looking for invisible matter. She was doing something that sounded much more routine, measuring the rotation speed of our neighboring Andromeda galaxy. Using a powerful new spectrograph, she could precisely measure how fast stars were moving at different distances from the galactic center, and everyone thought they knew what she would find. Think about our solar system. The sun has almost all the mass, so planets close to it, like Mercury, have to move incredibly fast to stay in orbit. Planets far away, like Neptune, travel at a much more leisurely pace. Gravity gets weaker with distance. It's a fundamental law. A galaxy should work the same way. All the bright stars, and thus most of the mass, are packed into the central bulge. So the stars on the far outer edges should be moving much, much slower. The graph of their speed should drop off, just like it does for the planets. Vera Rubin measured the stars at the edge of Andromeda, and they were moving too fast, way too fast. In fact, they were moving at almost the same speed as stars much closer to the center. The rotation curve wasn't a curve, it was a flat line. This was a complete violation of everything we thought we knew. It was like finding out that Pluto orbits the sun at the same speed as Earth. The only possible explanation was that the visible galaxy was just the tip of the iceberg. It had to be embedded in a massive, invisible halo of dark matter, whose gravity was gripping those outer stars and keeping them from flying off into space. This wasn't an error. Rubin and her team measured dozens of other galaxies, and they all told the same story. Every single one was spinning too fast. Every galaxy was encased in an enormous halo of invisible matter. Zicky's ghost was real, and it wasn't a minor component. The math was undeniable. This dark matter had to outweigh all the normal matter, all the stars, gas, and dust, by a factor of at least 5 to 1. Our universe wasn't what it seemed. It was a phantom version of itself. But if we can't see it, how else can we prove it's there? The answer comes from Albert Einstein. His theory of general relativity tells us that mass warps space-time. And because light travels through space-time, a massive object can act like a lens, bending the path of light from things behind it. This is called gravitational lensing, and it's one of the most powerful tools in astronomy. It allows us to weigh things we can't see. When we look at huge clusters of galaxies, we often see the light from even more distant galaxies behind them stretched and distorted into beautiful arcs. We can measure how much that light is bent, and from that we can calculate precisely how much mass must be in the cluster acting as the lens. And every single time the result is the same. The mass needed to create the lensing effect is 5 to 10 times greater than the mass of all the stars and hot gas we can see. Gravitational lensing allows us to draw a map of the invisible. We can see exactly where the gravity is, and it's not where the light is. The absolute smoking gun, the definitive proof that dark matter is real and separate from normal matter, comes from a cosmic collision called the Bullet Cluster. It's two galaxy clusters that have recently passed right through each other. The normal matter, the vast clouds of gas, smashed together and slowed down, creating a shockwave of superheated gas in the middle that we can see with X-ray telescopes. But the dark matter, which doesn't really interact with anything except gravity, appears to have cast right through itself like two ghosts. Using gravitational lensing, we can map where most of the mass is. And it's not with the normal matter in the middle. It's out on the sides, with the ghost clouds that kept on going. The stuff with all the gravity is in a completely different place from the stuff we can see. When we look at huge clusters of galaxies, we often see the light from even more distant galaxies behind them, stretched and distorted into beautiful arcs. We can measure how much that light is bent, and from that, we can calculate precisely how much mass must be in the cluster, acting as the lens. And every single time, the result is the same. The mass needed to create the lensing effect is 5 to 10 times greater than the mass of all the stars and hot gas we can see. Gravitational lensing allows us to draw a map of the invisible. We can see exactly where the gravity is, and it's not where the light is. The absolute smoking gun, the definitive proof that dark matter is real and separate from normal matter, comes from a cosmic collision called the Bullet Cluster. It's two galaxy clusters that have recently passed right through each other. The normal matter, the vast clouds of gas, smashed together and slowed down, creating a shockwave of superheated gas in the middle that we can see with X-ray telescopes. But the dark matter, which doesn't really interact with anything except gravity, appears to have passed right through itself like two ghosts. Using gravitational lensing, we can map where most of the mass is, and it's not with the normal matter in the middle. It's out on the sides, with the ghost clouds that kept on going. The stuff with all the gravity is in a completely different place from the stuff we can see. All right, so we know this invisible stuff exists, but what is it? Let's start with what it's not. It isn't just normal matter that's hard to see, like rogue planets, cold gas clouds, or dead stars. This kind of baryonic matter, the same stuff you and I are made of, still interacts with light in predictable ways. It would absorb, block, or emit radiation that our telescopes would have picked up by now. The universe would look very different. So it's not that. What about more exotic, compact objects? Maybe the halo is full of primordial black holes or faint, failed stars called brown dwarfs. These are known as machos, massive astrophysical compact halo objects. For years, astronomers conducted massive surveys, watching millions of stars, hoping to catch a macho passing in front of one. Such an event would cause a brief, predictable brightening of the background star due to microlensing. They found some, but nowhere near the number needed to account for all the dark matter. So machos are out too. This leads us to a truly profound conclusion. Dark matter has to be made of something completely new. It must be a type of particle that isn't part of the standard model of particle physics, our otherwise perfect theory of all the fundamental particles and forces. This isn't just finding a new planet. This is discovering a fundamental new ingredient of reality itself, a particle that has shaped the cosmos from the very beginning. For a long time, the leading candidate was the WIMP, the weakly interacting massive particle. The name is a perfect description. Massive means they would have enough gravity to form the halos we see. Weakly interacting means they don't feel the electromagnetic force, so they're invisible, and they barely interact with normal matter at all. Right now, billions of WIMPs could be streaming through your body and you would never notice. They are the perfect cosmic ghost particle. But there's another contender, the axion. Axions are the opposite of WIMPs. They would be incredibly, almost unbelievably lightweight, but there would be a staggering number of them, forming a vast, coherent wave that fills all of space. Axions were actually invented to solve a completely different problem in particle physics, but it turns out they have just the right properties to be dark matter. They're light, they don't interact, and they could have been produced in huge quantities during the Big Bang.
So, how do you catch a ghost? One way is to build the quietest place on Earth and wait. These are direct detection experiments. Buried a mile underground to shield them from cosmic rays, experiments like Lux Zeppelin use huge vats of ultra-pure liquid xenon as a target. The idea is that out of the billions of dark matter particles passing through the tank every second, one might, just once in a blue moon, score a direct hit on a xenon nucleus. This would create a tiny flash of light and knock loose a few electrons, which their hypersensitive detectors are waiting to see. So far, after years of listening, the universe has remained silent. Another approach is to look for the wreckage. If dark matter particles can collide and annihilate each other, they should produce a shower of particles we can see, like high-energy gamma rays. So we point gamma ray telescopes at places where dark matter should be very dense, like the center of our galaxy, and look for an excess of gamma rays with a very specific energy signature. It's like looking for smoke to find an invisible fire. There have been some tantalizing hints, but nothing that definitively screams dark matter. If you can't find it in the wild, maybe you can make it in a lab. At the Large Hadron Collider, we smash protons together at nearly the speed of light to recreate the energy of the early universe. The hope is that in the debris of these collisions, we might create dark matter particles. We wouldn't see the particle itself, but we'd see its effect. We'd see energy going into the collision and less energy coming out. The missing energy would have been carried away by the invisible dark matter particle we created. The hunt is on, but so far, no luck. Here's the most amazing part. Even though we don't know what it is, we know we wouldn't exist without it. When we run simulations of how the universe grew, we simply cannot form galaxies as quickly as they appeared without dark matter. Normal matter on its own is too hot and messy. Dark matter, interacting only through gravity, collapsed first. It created a vast invisible cosmic web, a gravitational scaffolding. Normal matter then fell into these pre-existing structures, like water flowing into a riverbed, and began to form the stars and galaxies we see today. No dark matter, no Milky Way. No Milky Way, no us. So, our cosmic census is starting to take shape. About 5% is the familiar stuff we're made of. About 27% is the invisible dark matter that acts as the universe's skeleton. But that only adds up to 32%. We are still missing 2/3 of the entire universe. And the discovery of this final, largest piece of the puzzle was even more shocking than the first. In the late 1990s, two teams of astronomers were trying to measure how much the expansion of the universe was slowing down. Everyone knew the Big Bang had kicked off the expansion, but they assumed the mutual gravity of all the matter in the universe was acting as a brake. To measure this, they used standard candles, specifically Type 1a supernovae. These are special stellar explosions that, for complex reasons, always detonate with the same intrinsic brightness. They are perfect cosmic lighthouses. By seeing how faint one appears, you can calculate exactly how far away it is. The plan was simple. Measure the distance and speed of many supernovae across cosmic time to map how the expansion rate had changed. Both teams worked for years, collecting their data, and they both found something that seemed impossible. The most distant supernovae were consistently fainter than they should have been. They were farther away than their speed indicated they should have been. There was only one way to interpret this. For the past 6 billion years, the expansion of the universe hasn't been slowing down. It's been speeding up. Take a second to absorb how utterly insane that is. It's like throwing a baseball into the air and watching it suddenly accelerate upwards into the sky on its own. Something was fighting against the gravity of all the matter in the universe, and it was winning. There had to be some kind of repulsive force, an anti-gravity woven into the very fabric of space itself. They gave this mysterious pressure a name: dark energy. The bizarre thing is, Einstein had predicted it 80 years earlier by accident. When he first developed his theory of general relativity, the equations told him the universe must be either expanding or contracting. Since everyone at the time believed the universe was static, he added a fudge factor to his equations to balance gravity and hold the universe still. He called it the cosmological constant. When it was later proven the universe was expanding, Einstein called this fudge factor his biggest blunder. And yet, it seems he was right for the wrong reasons. Dark energy behaves exactly like his cosmological constant. It might just be the energy of empty space itself. The evidence for this accelerating expansion doesn't just come from supernovae. It comes from the oldest light in the universe, the cosmic microwave background, the afterglow of the Big Bang. This ancient light isn't perfectly uniform. It has tiny hot and cold spots. The size and distribution of these spots are a perfect fingerprint of the early universe's properties, including its total energy and matter content. And the data from our most precise satellites like Planck are crystal clear.
The numbers only work if the universe is made up of about 5% normal matter, 27% dark matter, and 68% dark energy. It all fits together. This paints a picture of a cosmic tug of war. For the first 8 billion years of the universe's life, matter was packed more densely together. Its collective gravity was winning the war, and the expansion was slowing down. But as space expanded, the matter thinned out. The density of dark energy, which seems to be a property of space itself, remained constant. About 6 billion years ago, we crossed a tipping point. The force of gravity dropped below the repulsive force of dark energy. The brakes failed and the accelerator was pushed to the floor. This dark energy will dictate the final fate of our universe. If it is a cosmological constant, the future is bleak and lonely. The accelerating expansion will carry all distant galaxies away from us faster than the speed of light. They will vanish from our sight one by one until our night sky is completely black beyond our own local group of galaxies. Stars will burn out, matter will decay. The universe will end not with a bang, but with a slow, quiet descent into a cold, dark, empty eternity. The Big Freeze. But there is another, more terrifying possibility. What if dark energy is not constant? What if its strength grows over time? This leads to a scenario called the Big Rip. In this future, the repulsive force would eventually become so powerful, it would overcome everything. It would tear apart galaxies, then solar systems. In the final minutes, it would be strong enough to overcome the forces holding planets and stars together. And in the last fraction of a second, it would become strong enough to rip apart atoms themselves, tearing the very fabric of reality to shreds. As if things weren't strange enough, our current understanding is facing a crisis. It's called the Hubble tension. When we measure the expansion rate of the universe today using nearby supernovae, we get one number. But when we use our model of the early universe, based on the cosmic microwave background, to predict what the expansion rate should be today, we get a different number. They don't agree. This might be a clue that dark energy is more complicated than we think, or that our entire model of cosmology is missing a piece. So, this is where we stand, living on a tiny island of familiarity in a vast cosmic ocean of ignorance. 95% of reality is composed of two substances we have only named, not understood. Dark matter, the invisible architect. Dark energy, the mysterious force driving our universe's fate. They are the biggest and most profound mysteries in all of science. And solving them won't just fill in the gaps in our knowledge. It will likely trigger a revolution in our understanding of reality itself. But we are not standing still. A new generation of telescopes and experiments is coming online, designed specifically to map this dark universe with incredible precision. We are building bigger traps deep underground and smashing particles with more energy than ever before. The answers are out there, encoded in the light from distant stars and the patterns of the cosmos. The greatest age of discovery isn't behind us. It's just beginning. The next time you look up at the night sky, remember what you're really seeing. The evidence of a grand, invisible universe waiting to be known. This whole story is a testament to how much we still have to learn. What part of this mystery blows your mind the most? Is it the invisible matter holding us together, or the strange energy pushing everything apart? Let me know in the comments. And if your brain enjoys being stretched by the biggest questions in science, make sure you subscribe and hit that bell so you don't miss our next journey into the unknown.